Well, welcome to the U.S. Geological Survey Hydrography Webinar Series. This is the first of several sessions scheduled to be given about every 6 weeks. My name is Jeff Simley, and I'll be your host for today's April 9th session. Also working with me on this webinar series is Al Ray. Al will be the host of our next session on May 21st. Al and I are the co-leads for the USGS Hydrography program. Logistics for today. We'll put everyone on mute during the presentation to help filter out distracting sounds. We will monitor the chat feature of WebEx for questions from participants and send chat to everyone. If we cannot address all the questions submitted, we will follow up with responses in the next few days. Also, we would appreciate your assistance with 3 short feedback questions after the presentation, but before we close, about the session and topics you will find of interest for future sessions. Our purpose for this webinar series is to share success stories from users who have solved real-world problems using hydrographic data, provide information on the NHD, WBD, and related products, and provide a forum for users similar to what might be encountered in a conference setting. Topics that we'll be covering in the series includes hydrology, resource management, pollution control, fisheries, emergency management, mapping, and elevation hydrography integration. The format of these seminars will cover use cases, underlying technology, rapid-fire sessions, and collect feedback. We'll hold the seminar series about once every 6 weeks. We'll provide information on the seminar series in a number of ways. First, you can go to the NHD website, nhd.usgs.gov, and click on Hydrography Seminar Series. Second, you will find information in the monthly NHD newsletter. Third, we will have information available through the American Water Resources Association. And fourth, we will have you on a mailing list from this seminar, and you'll receive notices by email. Fifth, you can sign up to get on the mailing list if you're not already registered. Our session today will be in 4 parts. First, I will give an introduction to the series by discussing the role of hydrography at the USGS. Second, I will give a brief history on how we got to where we are today with the NHD. Then Dr. William Samuels will give a talk on river spill and the Incident Command tool for drinking water protection. That will be followed by a discussion you are invited to have with Dr. Samuels. Let's start by looking at how hydrography fits into the USGS. At the U.S. Geological Survey, Core Science Systems is an organization that provides data about Earth and its resources in a format that is understandable and accessible. One of the ways it does this is through the National Geospatial Program, which organizes, maintains, and publishes the geospatial baseline of the nation's topography through the national map. The underlying foundation of topography consists of surface elevations and the hydrography that shapes and is shaped by that surface. The USGS provides a geospatial fabric of surface elevations through its 3-dimensional elevation program, or 3DEP. Complementing this, the USGS provides a geospatial fabric of hydrography in 2 data sets. The first is the National Hydrography Data Set. The second is the Watershed Boundary Data Set. Combined, these 2 data sets identify water courses on the landscape and the drainage basins that contain them. Combined again with elevation data, we have created a highly detailed and accurate account of the foundational elements of the landscape. This is available seamlessly across the nation, is easily accessible to all, and ready to use by all sectors of science, resource management, and commerce. Importantly, these data are designed to allow us to perform analytics, thereby increasing the power of the data beyond mapping and giving us answers to many questions about the landscape. An example is the ability to navigate the nation's waterways and instantly measure the length of networks. We can also look at elevation data and make landscape measurements, such as instantly determining the area of a basin, and taking that one step further to generate drainage catchments. Capabilities of these data have led to powerful interactive analytical systems like StreamStats that can estimate the water flows of rivers and streams for a wide variety of conditions. 3DEP, the NHD, and the WBD are all critical components that make this possible. Similarly, the NHD Plus uses these data along with other landscape characteristics to estimate flow on a massive scale across the nation and provide this in an enhanced geospatial data set. A great example of integrating geospatial data to understand complex analysis is GeoFin, developed by the U.S. Fish and Wildlife Service for examining the ability of fish to reach upstream spawning grounds. This begins with the USGS NHD to represent streams and rivers. These rivers and streams have been enhanced by the U.S. Forest Service, working as stewards of the NHD data. Those streams declared impaired are mapped by the U.S. Environmental Protection Agency using the NHD. The U.S. Army Corps of Engineers identifies dams on rivers that have the potential to block fish from swimming upstream. The U.S. Fish and Wildlife Service and the state of California have identified locations on the NHD where fish movement is potentially restricted by culverts, waterfalls, and rapids. Another application of the NHD is to identify water rights in the state of California to make it easier for the state to adjudicate water rights. In a similar manner, the U.S. EPA uses the NHD to identify the location of water discharge permits and helps manage the allocation of permits. The NHD that makes these and other systems possible maps streams, rivers, lakes, ponds, ditches, water diversion, stream gauges, dams, and a range of other surface water features that would typically be shown on topographic maps. It also identifies the flow direction of water that makes upstream, downstream cause and effect analysis possible. One of the major issues in mapping of hydrography is to determine how much detail to show. The fractal nature of flow networks, as it collects water on the landscape, means that we can map streams down to an extremely dense level. But the cost to collect, manage, and utilize data is beyond the resources available. So we reduced the stream portrayal to a manageable level. This is an example of streams that would be collected at 1 to 100,000 scale. As we increase the resolution of the map to 1 to 24,000 scale, there is a need to show even more streams in a denser pattern as we see here. Then as we increase the resolution of the map even further to 1 to 5,000 scale, a new level of density can be generated. The question is where to stop. That can be hard to say because scientists and managers are analyzing the landscape at ever enlarged scales and demanding more and more data. Meeting this need are vastly improved methods to obtain this level of data at costs that are generally affordable. Next, we'll look at a brief history of hydrography data that has given rise to the NHD of today. The mapping of water in the United States has a rich history. That history could be said to begin before the New World was discovered by Europeans. This petroglyph found in the lands once occupied by the Shoshone people in Idaho is known as Map Rock and is believed to map the Snake River. These pre-European maps can be said to make up the first era of mapping water on the continent. The second era of mapping water in North America started in 1507 with European exploration that lasted through 1878. Throughout this period, the most prominent feature found on maps was rivers. Then, in 1879, the U.S. Geological Survey was created to, quote, begin a scientific classification of the national domain for general information, unquote. The great surveys of the West were discontinued and brought under the auspices of the USGS. In 1889, funds were allocated specifically for topographic surveys. The first maps were 1 degree in size and used a scale of 1 to 250,000, but this quickly transitioned to the 30-minute by 30-minute size at 1 to 125,000 scale, as seen on this map of Little Rock, Arkansas. These maps would launch the systematic coverage of the United States with quadrangle topographic maps. By 1935, the The USGS is producing maps at 1 to 24,000 scale in a 7.5 minute by 7.5 minute format that defines topographic mapping in the United States to this day. The area covered by this map is 1/16 of the previous map and shows the land to the northwest of Little Rock in the North Little Rock quadrangle. A contour interval of 10 feet means great precision of the topography, including hydrography. Maps of the 1930s and 40s still use ground survey methods. In the 1930s, aerial photography was introduced into the map-making process. In the 1940s, the science of photogrammetry, the measurement of photos, matured to the point where it could be used systematically in mapping. This is the 1954 edition of the North Little Rock Quad, which incorporated photogrammetric methods. Photogrammetry made updating the hydrography much easier. This 2014 edition introduces the US Topo product and a new type of mapping. The US Topo process uses digital mapping techniques to construct maps in which all the base information, including hydrography, has been converted to digital format, and the finished map is then produced in an all-digital environment. We'll call this period of mapping National Large-Scale Systematic Mapping that started in 1879 and lasts to the present time as Era 3 in the mapping of hydrography. It is characterized by a number of revolutions in technology that has allowed increased resolution, increased accuracy, increased frequency, and decreased the resources necessary to map the country. Overlapping with the third era of mapping is the fourth era, characterized by geographic information systems. This began in the 1960s with computers and computer printout graphics. At first, digital maps were rather crude, but they were a milestone. The age of hand-drafted maps is now giving way to computer-drafted maps. This is a map of water turbidity in Lake Mendota in Wisconsin. The technology steadily improved throughout the 1970s with vector plotters. In the 1980s, mapping was transformed by mini-computers and interactive computer graphics. This allowed cartographers to rapidly create different mapping scenarios and made integrating, relating, measuring, and analyzing data much faster and more accurate. In the 1980s, the systematic digitizing of maps became commonplace. Maps now existed as databases within a computer environment. To better manage the information, data themes were created. Water on most maps was printed in blue. The materials used to make the blue printing plate were digitized separately from other materials. The information collected in this manner was organized in separate database files. The files with water were referred to as the hydrography theme. Maps made using geographic information systems were composed of multiple themes. Hydrography was established as one of the primary themes of topography. The USGS became heavily involved in digital mapping when the U.S. Census Bureau produced a digital hydrography theme for their 1990 census maps. These maps were produced at 1 to 100,000 scale and provided nationwide coverage. They were called digital line graphs, or DLGs. The U.S. Census version of this data was known as Tiger data. In the 1970s, the Environmental Protection Agency had begun to model the flow of water in a geographic information system using hydrography data digitized from 1 to 250,000 scale aeronautical charts that had been photo-reduced to 1 to 500,000 scale. The EPA modeled the flow of water using a flow network in a dataset called RF1. By the late 1980s, the RF3 at 1 to 100,000 scale was developed by the EPA's Office of Water to provide a nationally consistent database to promote comparability for national, regional, and state reporting requirements, such as those found in 305B and other sections of the Clean Water Act. In the RF3 and RF1, streams were broken into segments. By piecing the stream segments together, river networks were established, and the flow of water throughout the nation drainage networks could be analyzed by computer modeling software. Combining digital cartography and hydrologic modeling in a geographic information system was a milestone in the evolution of geographic science. In 1993, the USGS and the EPA realized they could combine their two hydrography programs to produce a new, improved flow network for the nation at 1 to 100,000 scale. It would improve resolution as well as produce a data set with a flow network suitable for environmental modeling. The combined data became the National Hydrography Data Set. Several years of joint development and planning by the USGS and the EPA finally led to the production of the National Hydrography Data Set, which was completed in 2002. The data set was an immediate success and was put to use by scientists and resource managers around the country. Even as the NHD was being produced, data users began to inquire about the possibility of increasing the resolution. The USGS had been digitizing its 1 to 24,000 scale maps, but digitizing and processing over 55,000 maps to provide nationwide coverage was too large of a task for a single agency. Growing interest led to a combined effort by states, federal agencies, and soon the 1 to 24,000 scale NHD, now known as the High Resolution NHD, was developed. By pooling resources of some of the 60 partnering agencies, the USGS was able to complete the production of High Resolution NHD for the nation in 2007. Paralleling the development of the NHD was the development of the Watershed Boundary Data Set, or WBD, jointly produced by the USGS and the Natural Resource Conservation Service. This data set defines the perimeters of watersheds, or drainage areas on the landscape, and was completed in 2010. The NHD and WBD are companion data sets that create a comprehensive water information system easily accessible by thousands of water scientists. They create a systematic approach to mapping rivers, lakes, and watersheds across the nation. During this period, the EPA was developing the 1 to 100,000 scale NHD in a significant new direction. All streams are different. Each one is uniquely characterized by the amount of water that flows through it. This is largely determined by the upstream drainage area, precipitation, and other landscape and geologic factors. If the drainage areas could be determined, it would be possible to include a variety of other factors into the model. We will estimate stream flow for each segment of a stream. This would give scientists a huge boost in their ability to model the nature of the nation's waters. To determine drainage areas, the National Elevation Data Set produced by the USGS was used along with watershed boundaries found in the Watershed Boundary Data Set. This new form of the NHD data set, integrating watershed data, elevation data, and landscape data, would become known as the NHD Plus, and was completed in 2006. It marked yet another milestone in the development of geospatial data. With stream flow and velocity estimates embedded in the NHD, the data set was transformed into an even more valuable and useful water information system that made major improvements in how water could be analyzed. The so-called fourth era, or GIS era, in the mapping and analysis of water, has made a huge impact on water science and management. What's next for the computer analysis of digital and hydrography data? LiDAR data will certainly play an important role in recording our understanding of the landscape. Also, the web will likely transform how we interact with geospatial data through the use of data delivery and analytical services. It is also probable that new innovations will influence the future of water analysis and create yet another new era in hydrography. It is safe to bet that these changes will come with greater and greater frequency as technology rapidly advances over the years. The NHD, WBD, and National Elevation Data Set produced by the USGS provide a triad of geospatial data to define the topography of the nation. This has revolutionized scientific hydrographic observation data collection and analysis. It is now possible to integrate many types of water information in geographic information systems and model the behavior of water to better inform us on how we manage our water resources. In today's talk, Dr. Samuels will be talking about West Virginia. Let's take a quick look at the NHD for West Virginia. Hydrography data was first digitized in the 1990s. By 2004, the high-resolution NHD was completed for the state. In the 2005 to 2012 timeframe, NHD data at 1 to 4,800 scale resolution was produced. In the 2013 to 2016 timeframe, the NHD is being used in the development of stream stats. The current focus of the NHD is the changing hydrography associated with surface mining. Our featured speaker today is Dr. William Samuels from the Center of Water Science and Engineering at Leidos Incorporated in Alexandria, Virginia. Dr. Samuels will speak on river spill and incident command tool for drinking water protection. Dr. Samuels is the director of the Center for Water Science and Engineering at Leidos, formerly SAIC. Leidos is a science and technology company working to address problems in national security, health, and engineering. He is currently the principal investigator for the Waterborne Transport Modeling Program sponsored by the Defense Threat Reduction Agency. So Bill, we'll turn this over to you.
Okay. Thank you, Jeff. Okay, I'm going to spend the next 20 minutes or so talking about an application of this tool called Icy Water, or the Incident Command Tool for Drinking Water Protection, and how it was used during the West Virginia chemical spill that occurred in January of 2014. As with the case of drinking water protection, when a hazardous material is released into a river that serves as a source water or drinking water supply, protection and contamination risk mitigation requires that information on the fate of waterborne contaminants be made available quickly to decision makers. And so what happened in January of 2014 was that a chemical spill of 4-methyl cyclohexane methanol, which is a foaming agent used in coal preparation, leaked from a tank at Freedom Industries into the Elk River. And this particular tank was about 1 mile upstream from the intake for the Charleston water supply. On January 19th, in the morning, about 8:15 or so, the Charleston residents noticed a sweet smell in the air, and the West Virginia Department of Environmental Protection began receiving odor complaints from Charleston residents. Later on that morning, at the Freedom Industries tank facility, 2 employees noticed a leak from a tank into the containment area surrounding it. And then later on that morning, about 11 o'clock, Department of Environmental Protection inspectors were there. They discovered the leak in response to the residents' complaints about odor. And when they arrived at the facility, they observed that this chemical, MCHM, was leaking through a concrete block, a containment dike. Later on, about noon, West Virginia American Water, which operates the water treatment plant for Charleston, became aware of the spill. They assumed that they could filter it, but by about 4 p.m., when their carbon filtration system could no longer handle this large amount of contamination in the water, the chemical began flowing through the carbon filter and entered the distribution system. Some additional information about what occurred at the site when inspectors went out there. They noticed a 4-foot wide stream of chemical liquid flowing across the floor of the containment dike and into the ground where the dike's wall joined its floor. And in addition, they found a approximately 400 square foot size stream outside the damaged white stainless tank area. And that material then leaked from the containment area into the ground and then traveled into the Elk River. And so you see in this particular picture a location of the tank facilities and the proximity to the Elk River system. What did we do? We actually received a call from the Greater Cincinnati Waterworks, which is a downstream facility that was concerned about that particular contamination. It was too late to do anything in terms of the Charleston area, but downstream utilities, and particularly Cincinnati, were concerned about protecting their water supplies. And so we started to make some runs of the icy water model. And so the model consists of a number of components. It's the NHD Plus that Jeff had just previously described. We couple that with USGS real-time stream gauges, so we can update the flows and velocities in the NHD Plus with real-time data. We have a database of assets, which includes drinking water intakes, municipal and industrial dischargers, emergency sites like fire stations, police stations, and other critical facilities like hospitals and schools. And then also a contaminant database, which has several hundred contaminants ranging from chemical, biological, and radiological materials with information about their toxicities, maximum contaminant levels, physical and chemical properties used for modeling. This system is GIS-based. Riverspill is the modeling engine that we use. A user interacts with it by identifying the location of the incident and defining the source term, whether it be instantaneous or continuous, how much was released, what was released, and then the Riverspill model will perform the hydraulic transport downstream. The outputs include downstream trace, which can be limited either by distance or time. That trace can be interrogated at any location to get a breakthrough curve, which is concentration as a function of time. And the system can also be run in the reverse direction to actually look at an upstream trace. So if you had a detection at some site and you're interested in the possible locations of where that might have come from, you can run the model in the reverse direction and start looking at upstream sources of contamination. So it's designed to work in emergency management cases as well as planning and contingency operations. So we set it up to try to use minimal input data, fairly simple user interface to get an answer very quickly to an emergency responder. By using the NHD Plus, we can perform hydraulic transport on any stream in the NHD Plus network. And we tried to select water quality state variables that control the major processes and parameters available from that national databases. So the system is designed to answer 4 basic questions. Where is the contaminant going? Is there a drinking water intake in its path? If so, when will it reach drinking water? And is the level of that contaminant high enough to be a human threat? The modeling principles behind icy water. With respect to the source term, a spill can be modeled as being an instantaneous release or a continuous release over some period of time. We make some assumptions about mixing. In this case, we're assuming instantaneous and complete mixing in the water column. The velocity data, we take the mean flow and velocity data from the NHD Plus, and we scale it based on measurements from USGS real-time gauges, or in some cases, flow forecasts and velocity forecasts from the NOAA, or National Weather Service, or River Forecast Center. We have a one-dimensional longitudinal dispersion model, and we also model first-order decay for chemical contaminants, and that equation is modified by temperature for biological contaminants. So this is what the interface looks like for this particular area. You see a map of the NHD Plus, the spill site there, and then very closely downstream is the location of the intake. You notice a number of gauges, and the one gauge that's very close, just downstream of the intake, was one of the gauges that we use for the real-time flow data. When we interrogate that gauge, in this case, we were able to retrieve real-time flow and also real-time velocity. In the user interface down in the lower left of this screen, we're reporting the flow from that gauge and the velocity, and then we're looking also at the average flow and average velocity from the NHD, and we make some scaling factors based on comparisons of those two flows, and we can then apply those scaling factors downstream until we get to the next gauge, and then we update it as we move downstream. Some outputs. Here we're actually looking at the entire flow regime from the where the spill occurred on the right-hand side of the screen, all the way down about 200 miles or so along the Kanawha River and then the Ohio River to Cincinnati. You can see a number of gauges there. The most immediate gauge was reporting flow and velocities. The other downstream gauges were reporting only water elevation. And so we were able to actually get from those other gauge sites information from the National Weather Service Ohio River Forecast Center, which we use to update the mean flows and velocities in the NHD+. Information about the water intakes is stored in the EPA's Safe Drinking Water Information System, or SDWIS. We can interrogate any intake in the system. It'll go out to SDWIS and bring up information about the population served, as well as contact information for the plant so that a notice or a warning could be called in or sent to them. So one of the first questions that were asked when the spill occurred was, where is it going to be in 24 hours? So this is a 24-hour trace from the site of the spill. We color the trace red, yellow, or blue, depending upon whether it's above the level of concern, in transition, or below the level of concern. And in addition, here you see on this map, we're plotting other assets from our database. So there are many other discharges downstream, both municipal and industrial. There are several toxic release inventory sites, a few hospitals, and other facilities that may be of interest to users to see what the environment looks like downstream. The types of results that we were reporting, we made some comparisons with measurements and observations that were being collected by West Virginia and other agencies downstream, so we could compare our model results with field observations. And we had that data for Charleston, for Huntington, West Virginia, where there was another intake, and also for Cincinnati. And we were comparing both the time of travel of the peak concentration as well as the max concentration, both from the observations as well as the icy water simulated forecasts. You can see from looking at this data that in some cases the results with respect to time of travel were very, very close. At Huntington, the observed peak was at 90 hours after the spill. The simulated results was 84 hours. And the concentrations were quite close in terms of peak concentrations. At Cincinnati, again, very close with respect to time of travel. The icy water model underpredicted what was observed with respect to the peak concentration. But still, the results were used by the decision makers to make some decisions about closing their intake and then reopening it. And here's the breakthrough curve for Cincinnati. And so what did the folks in Cincinnati do with some of this information? The water utility shut down its intake shortly before midnight on Tuesday, January 14th, which was 136 hours after the spill, assuming the spill began around 8 a.m. on January 9th. And this was a precautionary measure to protect its drinking water supply. The contaminant MCHM was first detected in the Ohio River near the Greater Cincinnati Waterworks Richard Miller Treatment Plant on Wednesday, January 15th, at approximately 7 a.m., which was 143 hours after the spill. And icy water predicted a time of arrival of the peak concentration about 150 hours, or 2 p.m. on January 15th. And then the Cincinnati Waterworks reopened their intake approximately 2 p.m. on January 16th, about 174 hours after the spill. So you can see all those events plotted on this particular graph here. The smooth curve is the icy water breakthrough curve forecast. The diamond symbols are the measurements, and you can see there that the peak time of arrival for the maximums corresponded quite closely, and the maximum observed peak was about 6 parts per billion higher than what was predicted by icy water. So there are a number of challenges associated with this particular event, particularly with uncertainty of input parameters. The spill duration, how long did the chemical actually leak from the tank, and what kind of release pattern did it show? Was it continuously releasing over a period of time, or were there sort of ups and downs? Did it ebb and flow? And exactly how much volume was released? Initial estimates were about 5,000 gallons, and then it went up to 7,500, and then finally it was agreed upon that there was a 10,000 gallons release. Toxicity levels of the contaminant were not well known. The CDC offered a toxicity level of concern of about 1 milligram per liter, and a lot of folks are using that as a benchmark. Also accounting for how much mass was lost through other downstream intakes. That was an unknown. And taking into account the accuracy of the actual measurements that were made for model updates and comparisons. And other factors with respect to trying to determine how the pollutant was delivered to the river, attenuation by the soil that it had to seep through. That was, again, another unknown. But there were a number of success factors that led to its use, the model's use, as well as observations for the Cincinnati Waterworks. The ability to use a national river network like the NHD Plus, coupled with real-time stream flow data and river forecast data, allowed simulations of the leading edge, peak concentration, and trailing edge, from the origin of the spill to hundreds of miles downstream. Having measurements along the way were useful for updating the model forecasts and for making comparisons with what was being predicted. And what we were finding that with respect to travel time, very, very good agreement with the peak concentrations, and at some of the intermediate stations like Huntington, very, very good agreement with the peak concentrations, and a little bit of, we were underestimating at Cincinnati. So we had a number of lessons learned for future experiences with this kind of event and this kind of modeling. Initial spill reports are often inaccurate, and you need to constantly update forecasts based on changes in the source term and also environmental conditions like the flow. Using both real-time gauge data and stream flow forecasts is important. Not all gauges that we encountered were reporting flow. Some of them were reporting just water surface elevation. And the water utility was basing their decisions not just on modeling forecasts, but also on field observations. That was important to corroborate what the model was predicting. And working collaboratively with local authorities, with water utilities and data providers were very useful in being able to get this modeling effort launched. So just a number of conclusions. For an event of this magnitude, I think this exercise showed the utility of a national level toxic spill model to simulate the entire pathway of the spill from the tributaries upstream like the Elk River onto the main stem of the Ohio River. and that the integration of this national level stream network, coupled with real-time stream flow and river forecast data as well as sampling observations, enable decision makers at this water utility to take appropriate action to protect their water supply. So finally, I just offer a little bit of further reading for more details about what I presented. Two recent papers. One, modeling the fate and transport of a chemical spill in the Elk River, which was recently published in the Journal of Environmental Engineering. And secondly, a paper published in the Water and Environment Journal on the Incident Command Tool for Drinking Water Protection. It gives all the details on the equations, modeling assumptions, and applications of this particular tool. So that concludes my presentation, and thank everyone for their attention.
Good, thanks a lot, Dr. Samuel. So let's open it up to questions via the chat. So I ask my colleagues in Reston, do you want to bring up some of these questions?
Right. So, Jeff, can you hear me?
Yeah.
Yeah. So if people don't see the chat, there's a little tool at the top of the screen that will open up a chat window, and you can ask your questions there. So we're, with the number of people on the line, we've decided not to open up the phone line itself. So if you want to ask a question, you need to type it into the chat and then send it to everyone. There's a little pull down above the chat box where it asks who you want to send it to, and everyone is at the very, very top of that list.
Okay, Dr. Samuels, we have a couple questions streaming in here. First one, can the articles you referenced be made available to the meeting participants? I guess we can post those to the NHD website, perhaps, right, Jeff?
Yeah, we sure can.
Okay, as part of the materials here. We also have a number of questions about access to the IC water tool. Where do you get it, and is it proprietary or licensed, that sort of thing?
Okay, I can answer that one. The tool was developed with funding from a number of different government agencies, including EPA, Forest Service, and the Department of Defense. And right now, it is maintained and developed through a contract with the Defense Threat Reduction Agency. And they can make that tool available to any federal, state, or local government agencies that request that's interested in requesting it. And I can provide the points of contact for making a request to DTRA for the tool.
Okay, so Bill, let's see, we had a question from the New York Water Science Center asking about how fast was the response, how fast were you able to respond to the spill and to start getting information to your clients?
Mm-hmm. Okay, we received a call from Cincinnati, and we were starting to get results to them within probably 12 hours or so. Once we were able to get information about the source term and the nature of the release, and that we kept sort of making updates several times a day to provide them with some updated information. The model runs took, depending upon how far we were doing a simulation. If we started at the site of the spill and went all the way to Cincinnati, model runs would take maybe 2 to 3 hours. If we were starting further downstream, let's say at Huntington, and then going to Cincinnati, we could, get results out in about 45 minutes to an hour. That gives you a feel for about the nature of our response.
So, Bill, I'd like to ask just a little bit of a follow-up. I know you've been working on the Open Water Data Initiative team that's looking at spill response. And can you give us just some idea how you think maybe we might be able to change the way that this sort of response happens so we can be better prepared in the future?
I think one thing that can change is sort of the architecture of the tool. It's right now basically it's a desktop application that runs as an extension to the ArcGIS system, and so a user then needs to have it set up on their system, have an ARC license, and have the data loaded. If that's all ready to go, then you can respond fairly quickly. If not, then you need to get all that software installed, get the data installed, and learn how to use the system. I think we could probably increase or cut down the response time if we had a web-based version of the tool where a user could log in. Then all the data is sitting there on the cloud, ready to go. You don't have to spin up an ARC license and load your data, and so I think moving to a more web-based type client-server environment would probably be the next iteration of this kind of application.
Okay, we've had several questions about the data that goes into the model and what kinds of things it can consider. For instance, would geomorphological data along the river have helped, or would it consider meteorological conditions or ice cover on the river?
Yeah, it's really set up to look just at the hydraulic transport in the river itself in a fairly with some simplifying assumptions, particularly one-dimensional longitudinal transport. So some of the geomorphology data along the riverbank, of course, is of interest, but right now the model would not be able to do much with that, except maybe if we knew something about how that might influence how much material might, from the total amount that was spilled, how much would not get into the river. So it could, use to help define the source term. With respect to meteorological data, yeah, as you recall from one of the graphs on the presentation, there was the flow was fairly low and steady in the tribs and in the Ohio main stem for like the first 24 to 36 hours, and then there was a rainfall event, and you started to see the flow increasing rapidly over time. So, the gauges then do see that signal from the rainfall data, and so the flows and the velocities are going to change as a result of that. So, through the gauge data, these types of rainfall and meteorological events are factored into the travel time.
Okay, Bill. So we have a question from Drew Grant in the Alaska DEC, and he asks, he never really heard how toxic the MCHM was, and what, so could you address how toxic that was, and whether you would need to change how you would model something that was either more or less toxic than that particular substance?
Yeah. what I recall was that there was not a lot known about the toxicity of this particular chemical when this occurred. I think there were some studies done on some animal studies with some numbers produced by the CDC. I think they came out with a level of concern of 1 milligram per liter, but that was, I think more of a guideline. The event actually did not cause any fatalities, any mortality, as far as I know, because I think a lot of people, when they started to notice that smell in the water, just wouldn't drink it. So from that perspective, it was a big inconvenience, as opposed to, I think, an event where a lot of people were getting sick. I think there are studies now that have occurred and may still be occurring to look more closely at the toxicity of this particular contaminant. With respect to, I'd have to go back to the literature to see what those studies have been.
Okay. We've had a couple questions about basically how long it takes to learn to use the model and whether there are training opportunities specifically for using this in an emergency response.
Bill, are you there?
Did we lose Bill?
It sounds like we did.
Well, perhaps this is a good time to open the poll then.
So I'll mention also that we'll get the answers to any of the questions that we didn't get answered here in the chat. Go ahead and type any more questions in there that you may have, and we'll get them answered directly to the mailing list of people who attended. And so we have a short poll, just 3 short questions about the seminar, and we'd appreciate it if you would take the time to give us some answers to those 3 questions before we close. I'll give it back to you, Jeff, I guess.
Yeah, and so just to remind everybody that this session is being recorded, and we will have the recording available at the NHD website. It's simply nhd.usgs.gov, and there's a tab there for Hydrography Seminar Series. Click on that, and you'll get information about how to access the recording of this and other information about this seminar. So, also point out that there's going to be another session on May 21st, hosted by Al Ray. It will feature a talk on flood modeling. And so, Al, do you want to say anything about that?
Oh, okay, sure. So Ed Clark from the National Weather Service, who's the flash flood coordinator for the Weather Service, will be talking about the work that is going on with the National Flood Interoperability Experiment. And so that's a big effort that's going on that's working on trying to develop real-time national hydrologic models that would be able to indicate where flooding would be occurring around the country. And so we'll have Ed on next month for that.
Yeah, thank you, Al. So thanks everybody for joining in on this presentation today, this webinar. A very fascinating talk by Dr. Samuels on the river spill. Very good application of geospatial data in solving problems, and so we are very appreciative of Dr. Samuels for that. Thanks, everybody, for joining. We look forward to having you join us for the next call on May 21st, and have a good day. Thank you.